Welcome everybody back to our whole users training session. Today we are very happy to introduce Asad Khan again, who is going to give us a tutorial on getting started with TensorFlow. As usual, please post your questions in chat. Damaimu, who is the systems engineer for HAL system, will be there online. He can help you to deal with any system related issues. And before you get started using HAL, make sure you follow this tutorial that is posted on the in the window right now, and we will post a direct link to it to launch your Jupyter Notebook session for the tutorial. All right, so Asad.
Yeah, thanks for that. So yeah, welcome everyone. Once again, like Vlad said, please make sure you follow the steps that I'm showing on the screen right now. Make sure you're logged into HAL. You have a Jupyter Notebook running, and you have Git cloned the second repository. So we are at tutorial 2 this time, Intro to TensorFlow, and the URL is listed here, and you just need to run this command from your terminal. So once you have cloned the repository to your home directory, if you go into the folder, you would see 2 notebooks. Layers, models, and training, and then tensors, variables, and derivatives. And if you're having any issues, please post in the chat, and Dawi would help you. I already see a couple of people raising issues. Let me try to address the first question. So the first question is, if someone is having issues accessing HAL on demand, is there a way to open the notebooks in Google? Well, I forgot to list, to post the links directly, but you can always download these notebooks and open it in Google Colab. So that's still an alternative you can try. But for now, I'm just going to assume everyone has access to the notebook. And so the order we are going to go through the notebooks is actually the opposite in which they're listed right now. We'll go through tensors, variables, and derivatives notebook first. Okay, so I just ask everyone to open this notebook. And once again, like last time, we need to pick the appropriate kernel or Conda environment to run this notebook in. So make sure if you don't see this Conda environment listed on the top right corner, Conda and OpenCE version 1.3.1, then make sure you go click kernel and change kernel. And once you scroll over change kernel, it will list all of the environments available to you. And so please just pick the OpenCE version 1.3.1. So this is just a crucial step. Make sure that you're in the right environment. If everything looks good, then we are ready to go. Okay, so before we start, let me just say a few words about what's the big picture goal of this tutorial. So I don't know if you came back to my last tutorial, but there the idea was to quickly give you some ideas about the fundamental building blocks of deep learning, and then quickly start building up neural networks to train on toy data sets, right? But now we're going to go a step below. I'm just going to assume that you have some background in deep learning, you know what a neural network is, and on a high level, how to train it. And we're going to go more into the fundamentals of building blocks of a deep learning API this time, okay? So TensorFlow is one API, PyTorch is a different API, and there are several possibilities here. But all of them have like some fundamental components that's universally true across different APIs. And my goal here is to just talk about them in order to enable you to start building more complex computations using these APIs. So it's one thing to deal with toy data sets and toy problems, but it's another thing to go into serious research. And for that, you need to have some understanding of like some deeper understanding of the underlying API. But to start with, last time I started with the linear regression example, and I said a single neuron in a deep neural network, you can think of it as a linear regression. And so this time I also thought maybe we can treat linear regression as a building block to motivate us to talk about different components of TensorFlow. So recall that linear regression is basically fitting to a straight line, y equals mx plus b. Now, usually, y and x are the variables mathematically when we look at the equation of a line. And m and b would be constant, right? That's how you define a line. But in data science, the perspective is flipped, right? We would have usually some fixed data. So some input variables x, some fixed input x and the corresponding output y. And the goal here is to learn the parameters m and b, okay? So we have no idea what m and b are. We just have a bunch of data, this tuple of x and y points, and we're trying to find the best fit line. So in deep learning, the perspective is flipped, and now our variables are m and b, whereas our fixed data, which could be numbers or vectors or matrices, are y and x. And these fixed data types in TensorFlow are called tensors. And we'll talk a little bit more about what they are. And the things you try to learn are variables, okay? So very quickly, we're just gonna go through the steps involved in linear regression through gradient descent. Basically, the first step is collect the predictions. So we first come up with some guesses for m and b values. Input are all xi values and collect the corresponding predictions. Then we decide on some kind of loss function. So since this is a regression problem, we're just going to compute mean square error, which is basically what is the squared distance between the predicted values and the ground truth values. Normalize that sum, and that's our loss. Then we compute the derivatives of the loss with respect to the parameters that we are trying to learn. So partial L, partial M, and partial L, partial B. This is, we compute this exactly, meaning we compute through the mathematical formula, and we don't do some kind of numerical approximation. And lastly, we update the parameters based on those derivatives, right? So once again, the gradient points in the direction of steepest descent. If we take a small step in the opposite direction, we'll start moving towards the minimum of the loss function, okay? So that's all that's involved in linear regression, and that sort of exposes what are the fundamental building blocks of any successful API, right? So first thing is the API needs to have some sense of fixed data types, tensors, and variable data types, variables. And then on top of that, it should be able to build a computational graph so that it can track what computations you're performing in order to find these derivatives automatically, right? So some fundamental building blocks of any deep learning API, I guess, would be tensors, variables, computational graph, and automatic differentiation, which are closely related to each other. So basically, what is a computational graph? If we open this up, y equals mx plus b, we can write it like so, where x is our node that takes in a fixed data type, w and b are parameters we'll try to learn. These two nodes, we'll start with some initial guesses, and then we multiply x with w, add it to b, that gives us some output. We put that and the ground truth into some loss function, that gives us the loss. So as long as we track these computations and keep a cache of the outputs at some of these nodes, then it becomes really easy to automatically compute the derivatives going backward in the backpropagation algorithm. Okay, so that's the big picture. Let's start with the simplest things, tensors. So what is a tensor? If you're familiar with NumPy or NumPy, these are very similar to NumPy arrays, okay? So meaning that they have a shape, a rank, and a size. What is a shape? It's basically the number of elements in each dimension. So let's say if I have a vector, if it has 3 elements, then the shape of the vector is just 3. Let's say if I have a matrix, the shape could be 3 by 3 or 4 by 3, 5 by 2, whatever, right? It just defines how many elements there are in each dimension. And then there is rank, which says how many number of axes do you have. So a vector has only one axis, so it's a rank 1 tensor. A matrix has 2 axes, so it's a rank 2, and so on. And finally, size basically tells you how many elements there are in the tensor. Okay. So basically very similar to NumPy arrays, right? These are all the things we also define whenever we are instantiating a NumPy array. An important thing is that a tensor will have a uniform data type. Okay, so if your tensor consists of ints, then all of the elements are going to be ints. You can't have mix and match, like some of the elements are ints and others are floats and strings and so on. The entire tensor has to be of a uniform data type. The only thing that's different from NumPy is that tensors are immutable. Okay, so once you assign some value to a tensor, you cannot change those values, right? If you reassign new values, then you would end up creating a new tensor, basically. Okay, so how do we instantiate a tensor? Basically, you can call tf.constant and then give it an array, basically the way you do it in NumPy, right? So I'm just giving a list of lists with certain numbers, and then we can print it. We can print its data type, and we can print its shape. So let's run that. Actually, let's run this first. Yeah, it takes a while to load TensorFlow, so sorry about that. But once it gets loaded, then everything should run relatively smoothly. Anyway, so you can inspect the data type and shape like so, but also you can specify the data type at the time of creation, right? So here, my list of lists consists of integers, basically. But if I specify the data type to be a float 64, then I can print the data type and it will automatically convert these ints to floats, okay? It's the same going the opposite. I can put floats in here and then specify the data type to be ints, and it will automatically convert the floats to ints. Okay, this is taking rather too long. Let's see what happens. Okay, so that's one way. You can also, just like in NumPy, you can have NumPy.zeros or ones. You can do something similar here. So this will give you a tensor of all zeros or ones, and you can specify the shape. You can also specify the data type again here. And you can also do any other constant, right? So you can give it some constant and specify the shape. So those are fixed tensors, predefined, but you can also randomly sample the values to initialize the tensor with. So again, in NumPy, you can get the values from a normal distribution or several different probability distributions. Same thing, same story here. So you can call it tf.random, and then there are a bunch of distributions available to you. So we can take samples from normal distribution. We'd have to specify the mean and the standard deviation, or we can get from the uniform distribution where we just define the interval, min and max value, or from Poisson, and so on. So once again, we can print these tensors, and this is what they look like, right? That's the zeros tensor, the ones tensor. These were all eight. Sampled from normal distribution, from uniform, and Poisson. Let's see. Okay, my notebook is giving me an error, so I'm just not going to run these cells. But if you're not getting any error, then feel free to run through the cells and reproduce these results. Okay, so let's just dive a little bit more into this difference between rank and size in case it's confusing. So like I said, a vector is a rank 1 tensor because it has only one axis. A scalar would be rank 0 tensor, matrix would be rank 2, and then you can have rank 4 or 5, however many you want. So let's just print. Also, if given a tensor, you can check its rank, its shape, or its size. So there are various calls that you can make on a tensor, and it would output the rank, shape, or tensor, or size. So our rank 2 tensor, of course, has rank 2, and rank 3 tensor has rank 3, as expected, of course. And then we can look at the shapes of rank 2 and 3 tensors. So this happens to be a 3x2 matrix. But once again, it could be 1x3 matrix or 10x10 matrix. That just gives you the size of each of the axes, right? But the rank stays 2 for a matrix. And then the size of the tensor is basically all of the elements, the number of elements within it. So the 3x2 matrix has 6 elements, and then this rank 3 tensor has 30 elements. Okay, so what can we do with a tensor? Once again, this is just very similar to NumPy arrays. So almost everything you can think of doing to a NumPy array, you can do to a tensor as well. So we can add 2 tensors element-wise. We can subtract them element-wise. We can multiply them, divide them, and we can also do matrix multiplication. For matrix multiplication, of course, we have to make sure that the dimensions are correct for the 2, because this is not defined for all matrices, between all matrices. There's also operator overloading, so you don't have to really call tf.add, tf.subtract, and so on. You can use the plus, minus, multiply, and add signs, just the way you use in NumPy. And then there's a bunch of other operations that you can do, and I'm not going to go through all of them, but you can look at the TensorFlow website that lists all of them. So for example, you can take the absolute value, or you can raise one tensor to the power of another, again, element-wise, and so on. So there's a bunch of more operations that you can do. But besides mathematical operations, there's also the matter of how to index or slice a tensor and reshape it. This again works very similar to NumPy. So we can use this colon syntax, where in NumPy, before the colon, we give the start index and the stop index, and then you can also give it the step size, right? So let's say if this is our tensor, then elements 1 to 3 are, we would extract them like so. Another possibility is you can call tf.slice. So again, colon, you can use colon method, or you can call tf.slice, and then you can give it the start index, and then the number of elements that you want to grab from that index on. So that's the size. Reshaping is also just like NumPy. So let's say I start with this tensor. It's just a one-dimensional vector. And then I can specify different shapes for it, and I can reshape it like so, right? I just call it again tf.constant, but just give it this shape argument, which I can change. And that would reshape the tensor. The important thing here is that if you reshape a tensor, this is not computationally heavy, because reshaping doesn't move the data in memory, basically. So there is no copying and deletions in memory, and so this is really fast and efficient. And finally, you can also increase the rank of a tensor or decrease it, at least the redundant dimensions, you can remove them, right? So to illustrate that, this last tensor here is rank 4 tensor. It has shape 2 by 2 by 2 by 2. And so we can add an additional dimension anywhere here, right? So if I can do that basically by calling tf.expand dims. I can add at the 0th axis, first or third, right? And so the result now would be 1 by 2 by 2 by 2, or if I add the first axis, first index, then I add an axis here, and so on. And then since these axes are redundant, we can also go back by calling tf.squeeze. So this, I hope also you have already seen in NumPy. And then final thing is, if you are, in some cases, you might want to do some operations in NumPy first and then convert it to tensor, or vice versa. And so there is this convenience function basically to convert tensors back to NumPy, or NumPy to tensors. Well, going from NumPy to tensor is very natural because a lot of times your data will be in NumPy format, for example, and then you feed it into a deep learning model, which expects tensors. So this is very natural direction. But luckily, it's very easy. So basically, you just pass that array into df.constant, and you can additionally specify the data type. And given a tensor, then you can just call .numpy method on it, and it will give you back a numpy array. Okay, so that's tensor. But the important thing about tensor is that these are immutable, right? So once you define a tensor, you can't change its values. So for instance, if I try to do this, I instantiated a ones tensor, and then I wanted the 1, 1 element to become 0. If you try this, it will throw this error, right? Item assignment is not supported. But on the other hand, we talked about deep learning models where we learn the parameters, right? And so all these parameters are tensors, which get updated over time. So how is that possible? And that's where basically the variables come in. Variables are essentially tensors, but you can update their values. So the way to create a variable is very similar. You can instantiate it by passing in a tensor to it first. So first, let's say I want my variable to be of a certain size and of a certain data type. Then I can first create a tensor of that size and data type, and then pass it into tf.variable. Okay, so that will initialize the variable, which I'm calling my variable here. And the rest of the properties are very similar to a tensor. So it will have a shape, a data type, and you can also convert this to NumPy back, and it will give you back a NumPy array. But the important thing now is you can assign new values, right? So this is the same variable, but I can call now .assign on it and just assign zeros, right? So I'm passing in a new tensor, and now the values of my variable will be updated to zeros. I can also do index slicing and indexing and just update the values of certain indices. So here, for example, I'm just updating the first column from zeros to ones. And two very convenient functions here are assign add and assign subtract, basically, assign add or assign sub. And you can pass a tensor and it will just subtract these values from your variable. And so this happens to be very important because during gradient descent, we'll just pass the gradient and update the variable by subtracting the gradient attenuated by some learning rate, right? So in a sense, this is an essential building block of a deep neural network, this operation here. Okay, so what else can we do? Well, almost every math operation that you can apply to a tensor, you can also apply to a variable, right? So I can create two variables here, and then I can add them or do matrix multiplication. But the thing to remember here is once you do a math op on a variable, it will give you back a tensor, not a variable, okay? So if you want to assign new values to a variable, you always have to call .assign or one of these methods on a variable. One thing that's important is a variable will have a fixed data type and shape. So once you instantiate your variable, this is something you cannot change, okay? So this is basically, if you're thinking of linear regression, once I define the size of my matrix that I'm trying to learn, I can't change the size of it anymore. So that will be fixed. I'm just going to be learning the parameters or the numbers within it. So if you try to, for example, assign a tensor of a different shape to your variable. So A was here 2 by 2, and now I'm trying to assign 3 by 2 tensor to it. It will, of course, throw an error because you cannot change the shape of a variable. Lastly, we can name our variables, right? So, of course, we have X and Y that are pointing to my variable, but then I can also give them the name property. And what happens when you build a deep neural network is all the variables in all of your layers automatically get assigned unique names. And so that's very helpful for later on calling and inspecting specific variables. Okay, so any questions up till now? Okay, if not, then, well, we have discussed variables and tensors. And now going back to linear regression, the next thing is, in order to update the variables, we need to find gradients and then update the variables. So how do we find gradients? Well, in the above example, we wrote them out. But if your computational graph is complex, meaning that there are millions of variables, hundreds of layers, then keeping track of gradients becomes sort of a problem. I mean, you can still write it out. You can apply the chain rule and find the formulas for all of the gradients, and then you can write a code to do this. But then every time you change the architecture of your network slightly, you'd have to repeat the whole procedure, right? So, and that's what we don't want to do. That's where computational graphs come in. If you define a computational graph, then it becomes very easy to automatically differentiate based on the operations, mathematical operations you applied in the graph. And then if you can dynamically define your graph, meaning you can write down all the operations and then do all that computation. So your graph dynamically grows and then keeps track of all the operations that happened, then that's super convenient because then I can change the topology of my graph and still compute gradients. So how do we do that in TensorFlow? Well, in TensorFlow, we can use something called gradient tape. So TensorFlow will not automatically track all of your mathematical operations in order to compute gradients, except if you do it within the scope of gradient tape. So anything that I do within the scope of gradient tape will get tracked, and then we would be able to automatically compute the derivatives. So what I mean here is I can, for example, instantiate a variable here, give it the initial value 5, and then I open a gradient tape scope. So I can call with tf.gradientTape as tape, and then I just square this x variable, right? So I'm calling y equals tf.square. Of course, I don't have to call it tf.square. I could have also written y equals x square. Excuse me. So now this operation that was done under the scope of gradient tape, this got tracked by TensorFlow. So now what I can do is I can compute dy dx by calling tape.gradient, and then I specify y with respect to x, right? So I want the gradient of y with respect to x. And then if I print out dy dx, I get back the expected value, right? Dy dx is 2 times x was 5 here, so we get back 10. So this is a very powerful thing, basically. Now, there are a couple of things to note here, though. Variables, even if you instantiate them outside the tape, they will automatically get tracked by gradient tape, but tensors will not. Okay, so the expectation here is that you would be updating your variables in a model. So you might need to compute gradients with respect to those, but tensors are fixed. You don't really need to compute the derivatives with respect to them. So by default, they're not tracked. But in case you want to track tensors as well, then you can just simply call tape.watch x. So here instead, x, instead of being a variable, is a tensor. But within gradient tape, I just tell the tape to watch this tensor, and then I can once again square it and compute the gradient exactly in the same fashion, and I get back the same result. Okay, now when we're dealing with deep neural networks, we'll usually have, let's say, for example, if I'm doing classification, I'll have like one output, but I might have millions of variables, right? So how do we compute the gradient with respect to millions of parameters? With tape, it's very simple. You just specify your output variable, and then you can give it a list of all the variables that you want to compute the gradient with respect to. So once again, in this example, this is the equation of the line. W and B are variables. X is just a fixed number. And so we can do y equals wx plus b. And then just for fun, let's also square it. So y square, the output we'll call z. And now I have two variables, w and b, and I want to compute the derivative of z, the partial derivative of z with respect to both w and b. So I'll just simply call tape.gradient of the output z with respect to both these parameters, and it will give me back dz dw and dz dv. And then you can basically check, this is still simple enough. We can write it out what the derivatives should be, and you can check that the values match. It's also possible to compute the derivatives of intermediate outputs with respect to intermediate variables. So for example, we can also compute the derivative of z with respect to y here. Okay, so we did it in 2 steps. So this is also possible. It's even possible to do second order derivatives. So for example, just a toy example here, distance equals half at squared, where a is acceleration and t is time. And then, as we know, velocity is the first derivative of distance with respect to time, and acceleration is the second derivative of distance with respect to time. So we can do this here. T will be a variable here. We can initialize it with 0. Acceleration, we can just fix it. So for example, if this is a falling object, we can just say 9.8 meters per second square. Then I'm defining a clock. So I can change the time and then assign time to t variable, right? So what initially I'm just interested in what's the velocity and acceleration, for example, 1 second after the object falls. So you can compute second order derivatives basically by opening up 2 gradient scopes. So I can open up the outer scope and then the inner scope. Then within the inner scope, I compute the distance and the speed. So this thing is, within the inner scope, I compute the distance. And then within the outer scope, I compute the speed. So when I do this operation within the outer scope, it's keeping track of this operation, meaning now I can compute the derivative of speed as well. So I can come out of the outer scope, and now I can compute acceleration, which is the gradient of speed with respect to time. So you can like change the clock here and find the speed and acceleration at different times. The acceleration, of course, should stay constant because we already specified it. should always be 9.8. You can find the speed. Anyway, just for illustrative purposes. Of course, so far, I think we have only dealt with variables that are scalars, but the variables can also be tensors of any rank. Could be matrices, vectors, anything. And you can still compute the derivative with respect to those variables. In that case, of course, the derivative will not be a number, but will match the dimensions of your variable. So if it was with respect to a matrix, then my derivative would also be a matrix. Okay, so yeah, there's a bunch more stuff we can talk about here. And for example, you can find the Jacobian and so on. And I would just refer you to the documents, TensorFlow documents at this point, if you want to explore further. But this just basically gives the fundamental idea of what a computational graph is and how do we compute the derivatives. So let's go back to linear regression. And if you came to my last tutorial, this is essentially how we started. First, I picked up a straight line, so y equals 2x. Then I just added some noise to it. And I started with some initial guesses for m and b. And then I just plotted my initial prediction, which I'm showing here. And then last time, this was my code block. So I pick a learning rate, number of epochs. And then for the number of epochs, I just go through these steps, right? So I compute the predicted value, compute the loss based on that predicted value, find the derivatives dm and dv, meaning of loss with respect to m and b, and then update these parameters. So let's just do that again, but instead of handwriting all this code for derivatives, let's make use of gradient tape. So everything is pretty much the same, except first I need to convert m, b to variables. So I had some initial guesses for m and b, and my input and output will be constants, tensors. Then the rest is pretty similar. For the number of epochs, I have to make sure that I do these computations within the scope of a gradient tape so that I can compute the derivatives. So once again, I compute the predicted values and then the loss, which is the mean square error. And now I don't need to know the formulas here anymore. So I can just simply call partial L, partial M, partial L, partial B by tape.gradient and give me the gradient of loss with respect to M and B. Once I get that, I can update the values for M and B by calling m.assign sub learning rate times that derivative, and then v.assign subtract learning rate times the derivative with respect to b. So if I run this, once again, you should find that the loss is decreasing. And after training, if you plot, then you should get a pretty good fit line. Okay, so I hope this gives you some sense of what tensors are, variables are, and how derivatives are computed in TensorFlow. So I'll take a moment here and see if there are any questions. So I'm seeing a couple of questions. There is one question that says that I assigned string variable to x, but it prints as string var 0. Why is this the case? Let's see, where did this happen? Okay, up here. Yeah, that's a good question. What does this 0 mean? I would try something like this, probably. It's unfortunate that I can't run the code myself. But let's say it's 2. And I also give it the name string var. And let's see whether this increments 0 to 1. That's my guess. Let me know. I'm not exactly sure. And then what is the role of persistent in tf.gradient tape? Unfortunately, I can't recall. I think my guess is it has something to do with resetting your gradient. So once the optimizer comes into play. But unfortunately, I can look it up and get back to you. I don't have an answer right now. And then can I make the screen a little bigger? Yes, I can. Sorry about that. Is this good? Okay, great. Okay, so so far we have like sort of automated computing the gradient, but this still kind of looks like a mess, right? So I have to like define the variables, of course, manually like so, and then do this thing m.assign sub learning rate times the gradient manually for each of these variables, right? And now the second question is, what if I have millions of variables? Do I really want to do this for millions of variables in my deep neural network? And the answer is no. And because we have some abstractions that can do that much more efficiently and cleanly. So that's where the idea of layers and models come in. And so let's go to the next notebook, which is labeled layers, models, and training. So let's open that up and I'll turn off my first notebook. Yeah, Jupyter Notebook is unfortunately very slow today. I don't really know what's going on, but let's try this again.
I think that's that file system which is overloaded at the moment. So maybe you want to try to open it on Google Colab.
Okay, I also don't seem to be able to download it too.
Maybe too many users using the machine concurrently.
Okay, I think what we can do is, while Tavi figures out the HAL thing, is I think we should be able to download the notebook here from the GitHub repository. So go there. There should be a way. If anyone knows a way to download Jupyter Notebook from GitHub, please post it in the chat. The only thing I know, I guess, is you can press raw and then copy paste it into a text file on your computer. Or yeah, good. Yeah, of course, you can also git clone on your own computer and open it. That reminds me, I also have this on a different machine, so I can run it there in the meantime. Okay, I'm just going to continue on a different machine. I hope you guys can download or git clone it to your own computer and then open it on Google Colab.
I think it might be something to do with our storage system.
Also, great comment by Rahul that you can also directly open the GitHub file in Google Colab. So if you just paste that URL into Google Colab, it should open it. Okay, so I'm hoping everybody can open the notebooks, but I'm going to start going through this. And if you can't open the notebook right now, just try to follow with me, and then you can, of course, rerun it on your own time. Or you can also just look at the outputs on the GitHub repo, because all of these cells are already run, so you know the expected behavior. Okay, so the idea with layers is that you can think of it as an abstraction that holds a bunch of variables together, and then also defines some computation on those variables. Okay, so we bring in both of those pieces together. So previously, I instantiated my variables W and B, and then within tf.gradient tape, I did a bunch of computation. The idea here is let's define both of those into a single unit. And the basic unit in Keras is just layers.layer class. Okay. If you want to go even deeper into this itself inherits from tf.module. So in case you don't want to work with Keras, you can also go to something different and define layers and models in more or less the same way. But I'm going to work with Keras. It's versatile and easy enough to use. I've personally never had to go to tf.module. Anyway, so we bring in together variables and computation together into a single abstract unit called layer. And then the nice thing about layer is that these will be automatically tracked by gradient tape, right? So I can define layers and then pass my input data through them. And if I do that within a gradient tape, then I can automatically find the gradient with respect to all of the variables contained within all of my layers. Okay, so that's the nice thing. And also, I'll just show you that once you define your layer, then doing the computation is aesthetically kind of pleasing. It visually looks like you're passing the data into your layer and getting an output instead of writing out all of the math ops. So how do we define a layer? Even before I do this, I should say Keras or TensorFlow, both of them have a bunch of layers predefined. I mean, usually almost anything you can think of or will need will be predefined there. But in unusual circumstances or special cases where you have to define your own layer, then this is how you do it. But it's also easy to like open it up and see what's happening within a layer in TensorFlow. So dense layer is already natively implemented in Keras, but let's define it again, and I'll just call it myDense. So there are two essential components. So this is a class, so we need an init method. And this is where you can instantiate your variables. So that's what I'm doing here. So for a dense layer, which is again a matrix multiplication, I'd have two variables, W and B. In single dimension, these are just numbers, but if I'm dealing with matrices vectors, then these will be matrices and vector. Right? Okay, so this is a variable, and I can initialize it at first by some random numbers, right? So I can go and sample a tensor from a normal distribution. So remember in the last notebook, I showed you we can instantiate tensors from random distributions. So this is a tensor here, and I'm passing this random tensor into a variable, giving it a name W, and that's my W variable. And for now, this is going to be a matrix. So I need to define its shape, so which will be fixed by in features and out features, right? So the shape of this matrix is dictated by my input space dimension and output space dimension, right? So if I'm mapping a vector from let's say 3 dimensions to 4 dimensions, then this matrix will be 3 by 4. Sorry, 4 by 3. And then this is the bias vector, right? Which will have, which will be a vector of the size of the output dimension. And it's common to initialize the bias vectors with just zeros, okay? So usually we initialize matrices or other tensors with random numbers and bias with zeros. So I instantiated my variables here. And then the second important essential component of layer class is call method, which defines what are the math ops we're going to do on these variables, okay? So this will require an input. So we'll always call it on an input x. And so given that input x, we're first going to do a matrix multiplication of x with w, and then add the bias vector, and that gives us our output. So I define that within call, and then I can also pass it through some nonlinear activation, right? So I'm just calling tf.nn.relu, but it's not really necessary. We can also define that in a separate layer. Let's say this is just a matrix, this affine transformation we're going to do here. Matrix multiplication and adding a bias vector. Okay, that's a layer. So once I define it, then I can instantiate my layer. So I just call my dense, give it a name, specify what are the input feature dimension and output feature dimension that fixes and initializes these weights and biases. And then calling it on a tensor is very simple. So here I'm just picking a random tensor. I'll call this my input, and I can just simply call simple. So I named my dense layer here. This instance is called simple layer, and I can just pass my input tensor into simple layer and give me my output. Okay. And then I can, for example, pass it once more. I can do z equals, let's do this one more time. There, y, okay. So now you can see like why this is kind of powerful. I don't have to write out the computation. I can just start stacking these layers together. And perhaps I need maybe some kind of nonlinear activation in between. So maybe y tilde will be that ReLU function, right? So for example, I have like this ReLU non-activation, and I just apply it on y. And then that's what I pass through another simple layer, and so on. And now this way I can start building my neural network. I can stack these layers together in a computation. Okay. One thing, if you came to the previous tutorial, you might remember that previously when we defined our neural networks, we didn't really have to define this in feature every single time, right? Every single layer. We had to do this for the very first layer, but after that, Keras was able to automatically infer the dimensions of all the subsequent layers. So how do we do that? For that, it's usually recommended that you delay the instantiation of these variables into this build method. And so this build method will not run until you pass an input into your layer. And then these will get instantiated for the first time. And depending on the shape of your input, that will dictate the shape of W and B here. And then your variables are fixed after that, their shape and data type. But a priori, you don't need to know the input dimension, which is dictated by your input. You can just specify the output dimension, which I'm calling units here, or this you can also think of as the number of neurons. Okay, so you can do this. So in your init, just specify your output dimension, but don't initialize your variables. Put that into build method. So once you do that, then when I'm instantiating my layer, I don't have to specify both dimensions. I just give the output dimension. And then I can like pass X through my flexible layer, and it will give me an output. And you can try changing the dimensions here. and it will still work, right? But of course, if you run this cell, like it will instantiate flexible layer again. So make sure you do that. Because once you pass an input, then these variables become fixed. And if you remember, variable shapes cannot be changed. Okay, so given a layer, you can always call .variable method on it, and this will give you back all the variables contained within the layer. So this is a very simple layer. It only has 2 variables, but layer could of course be much more complicated with many more variables. And so you can inspect them by calling this. You can also pick a variable by their name. And so for example, self.b, I just named it b. So you can also call flexible layer.b. And so by name, you can also pick up the variables within that layer. Now by default, like if you do any computation within a gradient tape with layers, all of the variables will be tracked. But sometimes you might want some variables in a layer which you don't want to train, right? You just want to fix them. And so that's doable. I mean, of course, one way is to, instead of building a variable, you can just fix a tensor. But another way is you can specify whether the variable is trainable or not. So that's also an option. So once again, I'm defining a dense layer. And here I want to fix my bias vector and only train the matrix W. So W, I just call trainable equals true, which is the case by default. So I don't really need to call this. But bias vector, I just specify to be false. So now when I take the gradient of my output with respect to this layer, it will only give me back gradients with respect to W and not B. Okay, the rest is the same. So I'm just doing matrix multiplication between W and input and adding bias. Okay, so now let's just double check that. I can call, so I instantiated my layer again here, this one, and I passed an input through it that fixed the dimensions of W and B. And so of course I passed a 2 by 2 matrix through this layer, and I get 2 by 16, right? Because I defined the output dimension to be 16. Now, of course, I can look at all of the weights in my layer. So I can just say my new layer.weights, it will return all of the weights, and there are 2. And then I can also just ask for trainable or non-trainable weights, right? So what is the length of my non-trainable weights? Only 1. And here I'm just printing out what are the trainable weights, which is of course this matrix, and which ones are the non-trainable weights. And that's this bias vector here. Okay. Any questions? So there is a conceptual question. If we know that the y is positively skewed, should we also draw on a positively skewed distribution for the variable W and B here? I mean, I would say it depends on your problem, right? If you want to respect certain symmetries, then you perhaps need to make sure that your operations respect the symmetries. But if not, then not necessarily, right? So yeah, I would say this is problem specific. But let me know if anyone has a better answer. So any other questions?
Yeah, I have a question about trainable. Is that something that you can assign during the layer instantiation?
Yes, excellent question. So that's yes. So you can also assign trainable to a layer directly. So here, for example, I can just say trainable equals false. And what this would do is it would set trainable equals false for all of the variables within that layer. Okay. So then like the entire layer becomes non-trainable. So the gradients won't be computed with respect to any of the variables in this layer. But again, if you want more fine-grained control over which variables are trainable and not, then you can go inside the definition of the layer and fix that. Or in fact, like after you call, even if after you instantiate your layer, you can always call your variable like so, right? Flexible.layer, flexible layer.p, and then you can do .trainable equals false. So even after instantiating, you can change the trainable property.
So potentially that could be useful with taking the existing model, chopping off the end, adding your little bits and deciding what is or is not trainable.
Exactly. And yeah, and that's like when you do transfer learning, so where you take a pre-trained model and then you adjust it on a related domain. This is essentially exactly what you do. You can decide a certain number of initial layers. You can decide for them to be fixed. So you just set their trainable to be false. And then the later layers, you can like update their parameters. Okay, so okay, let me just go through one more question here. Dropout is also defined during layer instantiation. Yeah, good question. So dropout, you can make it part of your layer as a mathematical operation, or you can also define it separately. And I think that's exactly what we're going to do next. So instead of doing dropout within the call, I am just defining dropout as a layer. Okay, so that I can then just add this to my graph. And dropout brings in another important concept, which is the operations that you perform within a layer can change, or you might want them to change depending on whether you're training the model or doing inference. Okay, so dropout is a prime example of that. During training, you actually do want the dropout to work, but during inference, you want to turn this layer off. Okay, so just as variables have the property called trainable, the call function will have a property called training. Okay, so you can set this to true or false. I think this, yeah. So during training, this variable will be set to true. And so then you actually apply a dropout. Right? So if you don't remember what dropout is, it's basically dropping off a certain number of inputs randomly based on the probability you give it. So I give it a certain rate, which is a probability, and then it just zeroes out a certain number of inputs. So let's say if my input is a 10-dimensional vector and my rate is 50%, then when I apply dropout, five of the neurons will become 0, right? And the rest will be just identity map. But this is usually what you want to do only during training. So you can think of dropout as just exploring different architectures in a sense. Each time you zero out certain neurons, so that gives you a certain architecture of your network. And then the next time you do forward pass, you will see a slightly different architecture. So this helps with overfitting. But during inference, now you have learned the parameters. You don't really want to do this. So you just turn it off. And so during inference, you will say training equals false. And so then you can have this if-else clause within the call. So that's what we do here. So I'm defining a dropout layer with 50% probability. My input is a 2x2 matrix drawn from normal distribution. And so output during training is I'm calling dropout on this, setting training equals true, and output during inference, this equals false. And then you can look at it, right? 50% of the inputs were zeroed out during training, but during inference, it's just identity. Okay, lastly, something that makes layers very powerful is that they are recursively composable. So basically, you can define a certain layer, and then you can define a more complex layer whose variables themselves are other layers, right? So instead of just having directly tf.variable as the variables of your layer, you can actually have other layers. So that's what I'm doing here. So let's look at this multiple layer perceptron block. So this is just going to be a layer that consists of a bunch of dense layers. So I already defined my dense layer up there. And now when I initialize this layer, I initialize 3 different dense layers. One goes to output dimension 32, another one also goes to 32, and then the last one goes to output dimension 1. Now when I call it on my input, I can sequentially pass it through all of those layers, right? So first I pass it through dense 1, then I can apply some kind of nonlinear activation, then through dense 2, another nonlinear activation, and finally through dense 3. Okay, but instantiating this layer and calling it is exactly the same. It doesn't care like whether inside it's composed of variables or other layers. You basically call the same thing, MLP block. You can draw some random input and pass it through your MLP layer, right? So now you can, if you call MLP.weights on this layer, it will give you 6. Okay, and why is that? Because each of these dense layers contain 2 weights. So 2 times 3, you have 6. So basically, this layer will have access to all of the variables of these underlying layers as well. And then trainable weights are only 3 because remember, when I defined this dense layer, I set only the W variable to be trainable, and B was not trainable. And so my input here was 3 by 64, but my last layer has shape 1. So of course, this will get mapped from 3 by 64 to 3 by 1. So everything works out. So any questions now? Because this is all I wanted to say about layers, and then we'll move to defining models and how they're different from layers. So there's one question: will dropout go under the def call? Under the call. Oh yeah, so here, I'm assuming you're asking if we wanted to apply dropout here, how would we do that? Yeah, that would be simple. First, you have to make sure that you instantiate your dropout there. So I'll just call self.drop is equal to, what did I call my dropout? Custom dropout. I don't know what happened here. Anyway, I think it was called custom dropout, and I specify the probability. And then let's say after this layer, I wanted to apply dropout, then I'll do x equals self.drop. Does that answer your question? Okay, great. Any other questions? Okay, if not, then let's move on to models. Now, what is a model? Okay, there is a couple of questions coming in, and I'll try to answer them next time. So how can I visualize layers? That's a good question. Let's wait until we can define models, and then I'll show you how. Okay, so we have our layers, but a neural network will be made up of a bunch of layers, right? The neural network will essentially look more or less like this. I mean, we're passing the input through a number of layers, and in a sense, this already is my model, right? So MLP block is a model already. but happens to be an instance of the layer class. Okay, so this is something we'll see. Models and layers in a sense are very similar. The only thing that's different is they inherit from different classes. And the model class happens to have a bunch of other utility functions that layer class doesn't. Okay, and those utility functions help with training the model, evaluating it, and saving and loading it. Okay, so that's the only difference. I could basically call this my model and train it, but then I wouldn't be able to use certain utility functions. And what are those? Well, those utility functions we'll discuss in the next section, which is about training the model. But right now, with that understanding that it's just about certain utility functions and that are available within the model class, but not layer class, let's move on to actually defining models. So I'm saying there are 3 levels of abstraction in TensorFlow when it comes to defining models. And it goes from the most abstract and easiest to the most lower level. And then obviously you have to do a little more coding to do that. So the easiest way is the sequential method. And it works in 2 equivalent ways. Basically, you have to call tf.keras.sequential and then pass a list of layers in the order that you want to apply them to tf.keras.sequential, and that will define your model. So what I mean is the first layer that the input should pass through, the second, third, and so on, and then the last layer. So it's just a list of layers that I'm passing. You would notice I'm passing this input layer, and this is not really a layer, but this is just a placeholder that defines, that fixes the shape of my inputs, right? So if I don't pass this, then none of the variables in the subsequent layers will get instantiated until I do actually pass an input through my model. And the only problem with that is then first you have to do that in order to inspect the model. But if you pass this layer, then it instantiates all of the weights. And then you can do something like model.summary, and it would print out a summary of your model. Okay. So you should try this. You can comment this out and define the model. But then if you call model.summary, it will complain that the variables are not instantiated. In which case you would have to do something like this. So you'll create a sample input, pass it through your model, and then you'll be able to call model.summary. Anyway, so that's one way. Another way is you call this line tf.keras.sequential, and then you can call .add method and add the layers sequentially once again, right? So these are basically more or less equivalent ways of defining a model. Okay, so this is the most higher level way of defining a model. It's extremely simple, but then therefore it also comes with certain limitations. I mean, here the limitation is that each layer will have only one input and one output. Okay, so each layer will be connected to one other layer, and then the output will go to one other layer. So if you're thinking of more complex architectures and topologies, then this will not work out. Yeah, I mean, if you have a shared layer, or you want to bring in multiple inputs at different levels or take out multiple outputs, then that's the sort of thing you can do with sequential API. So that's the top level. But what if we want to do something more complicated? Then the functional API comes to rescue. You can always go to this. And to be honest, this is, at first glance, it's just as simple as sequential. Okay, so let's try to implement this model again in functional API. And what do we do? Well, first we define our input. So again, we just call tf.keras.input layer. Then we pass it through a layer. So we're doing 2 steps here together. I'm instantiating a layer, a dense layer with 32 units, and then passing the input through it. And that gives me an output. Then I'm instantiating another layer, ReLU, and passing X here, and that gives me another output. And so this is the sequence in which the input is going, right, to the output. And finally, this is my final output. And this is just a dense layer with 1 neuron. Okay. Now, to define the complete model, all I have to do is call this tf.keras.model. I just have to like specify what are my inputs, what are my outputs. So my input is this, and my output is this, and I can give my model a name. And then I can similarly call model.summary, and should be exactly the same as up there. So at first glance, it looks very similar and very simple, but the power comes in with more complex topologies. So let's say if I had multiple inputs and multiple outputs, how would I do that? With sequential, I can't do it, but with functional API, I can. So this is just a toy example. It doesn't really have to make sense, but I had to come up with something. So let's say on any given day, my model takes in a few weather data variables like pressure, precipitation, the percentage of the sky covered with clouds, wind speed, and so on, and then tries to predict the temperature and humidity for the same day. Right? So this is multiple input, multiple output model. So how do we define this? Okay, with functional API, very simple. So note up here, we just had one input, but now we have 4 inputs. So we'll define 4 input layers. So my pressure input is an input layer, has shape 1, because this is just a numerical value. Precipitation is also numerical value, and so on. And I'm giving each of my layers names. Then I want to, for example, concatenate the pressure and precipitation inputs together and pass it through a bunch of dense layers. So I can do this. I can call concatenate method on my pressure and precipitation input. That will just concatenate the 2 vectors together. And I pass it through 2 dense layers. Okay, so now I'm in an intermediate space where I've just processed pressure and precipitation. Same thing, I can have another branch that just processes the clouds input and wind input, pass it through a bunch of dense layers, and I get another output. So right now I have like 2 branches, right? This branch is taking in pressure and precipitation. This branch is taking clouds and winds and processing them. I have 2 branches. I need to combine them together and go to the output. So here I'm just concatenating the branches, X and Y. So this is my last output on the X branch. This is the last output on the Y branch. I concatenate them together, pass this result through a bunch of dense layers. And now I need to split once again. I need to create 2 branches, one for temperature. This will give me the temperature output. So this branch takes this common tail, right, Z, and then also one branch that predicts humidity. It also goes from Z to humidity. And now I can define my multiple input output model like so. Once again, I can say tf.keras.model, but now my inputs is a list, right? Remember, I have 4 inputs: pressure, precipitation, input, precipitation, clouds, and wind. And I have 2 outputs, temperature and humidity. Once again, I can give it a name and print the summary. Okay, summary with this kind of topology might be a little hard to disentangle, right? So summary is by default sort of linear, but you can pay close attention to what each layer is connected to, and that can help you decide what should this model look like. So the first 4 are inputs, they're not connected to anything. Then this concatenate layer takes pressure and precipitation, this one takes clouds and wind, and then this takes the first concatenation, this one takes the second, and so on. But there's also another convenient utility function, which is called plot model, and that does the job much better. So if I call plot model on this model, then you can see it visually very nicely. I have 4 inputs. Pressure and precipitation go through a bunch of dense layers. This is my left branch. Clouds and winds go through the right branch. Then I bring those 2 branches together, a common tail branch, and then they split out again. So now this is a fairly complex topology, but you can see how easy it is with the functional API to define it. So that's the second method. It's a if your topology is more complex, then this gives you more power to define it compared to sequential. And the most lower level way of classifying, defining your architecture is subclassing. So this method is more or less exactly the same as when we defined our custom layers. The only thing different is instead of calling tf.keras.layers, we're just going to call tf.keras.model because that's the class we're inheriting from. But the rest is exactly the same, right? So I initialize, instead of giving a bunch of variables, I'm giving a bunch of layers, dense1, dense2, dense3, and then a call method, which basically is defining the computation more or less the same as I did with the functional API up here. But with this, you can do if-else clauses, and it gives you a little more control over the flow here. So I can do something like if inputs is less than 0, then I want to do this computation. Else I can do, oops. Else I can do something else, right? I can define maybe I don't need ReLUs, for example. I can comment this out. So it gives you, now this is like the most lower level, so you can do much more complex things with this way of defining a model. Okay, so that's it. Basically, once again, then you instantiate your model exactly the same way that you instantiate your layer. And you can pass your inputs through the model and it will give you an output. And you can call model.summary and you get a summary out here. One thing I haven't figured out, and if you figure out, ping me anytime, why do we get this multiple on the output shape in the summary method? I don't really know. Because once I call it on an input, it should really fix the shapes, but or perhaps it's because of this if-else thing, right? The shapes can change. I'm not sure. It's a good thing to look into. So that's 3 ways of defining a model. So let's take another short break here, and if you have any questions, happy to answer. Okay, so there's one very good question, which is every layer between input and output layers captured by the model as part of the model in the functional API? So going up, let's go up here. And so is every layer captured as part of the model? And the answer is yes. And another beauty of this method is I can define multiple models with just one logic. So let's say I wanted another model right here. So I can like call this Z, and then this goes here. So one model is where the input and output, so it captures all the layers, but maybe I want another model that only captures half of it. So then I can do, my input is still input and my output is Z. So let's just call this first half. Right. So I just had to define the logic once and I can define 2 models. And then of course I can also define a second half model where perhaps the input is Z and then the outputs are outputs. So now this model is just capturing these layers. This model is just capturing these layers. And the first one, of course, captured all the layers. And then how do I add direct connection between non-consecutive layers? I mean, the layers don't have to be consecutive, right? The only thing is maybe like you can just change the names here. So let's say I want to add a layer at this point and then define a few more layers, right? So I can just pick X here and start working from there. So I can define layer 3 to X. So where layer 2 could be anything. That gives me a new output, right? Yep. So okay, let's go to the exciting part. So far we have talked about tensors, variables, gradients, layers, models, but this is all just the skeleton, right? In the end, we want to train it. So how do we train a model? And again, TensorFlow has 3 levels of abstraction, right? So it just depends on what's your use case, how familiar you are with the API. You can pick any of these 3. So new users, I would recommend, again, like pick the most abstract, easiest level. And then as your use case evolves, start looking further into like more lower level ways of training. So once again, we're going to talk about 3 levels here, going from the most abstract and easiest. So for this, I'll just fix the data set and model because we don't need to change those. We're just going to change how we train it. So for the data set, I'm just picking the MNIST data set. If you came to my last tutorial, you know more or less what this looks like. These are just handwritten digits, pictures of handwritten digits. And we are training a model that basically classifies the images correctly. So the model is able to say what digit is in the image. And for this, we'll define a simple convolutional neural network. Again, if you came to my last tutorial, you should be familiar with this. If not, you can look it up. It's pretty easy. Convolution is just another layer, another type of layer. And I'm using the architecture that I used in my last tutorial, basically. So a bunch of convolutional layers, max pooling layers, and then fully connected layer at the end. And then we have 10 neurons in the last layer because we're trying to classify 10 different digits. Okay, let's just fix those. We don't need to change those 2. Now we're just going to look into different methods of training. So the easiest, most abstract way is just this .fit method. So as soon as you have defined your model, then you can call .fit method on model. And this is where model class differs from layer class. So you can't call .fit on a layer. You can call it on a model. Okay, so, but before we call it, there's a couple more things we need to specify. We need to specify the optimizer, which is which flavor of gradient descent we want to use. We want to specify the loss function. This will be dictated by what kind of problem we have. So for regression, mean square error. For classification, we'll have categorical cross entropy. And then any additional metrics we want to keep track of, right? So the loss is what gradients are calculated with respect to. But then you can also track metrics, right? So these metrics will not play a part in updating the parameters of the network, but might be nice to just look at. So for metrics, we can also add like something like accuracy. Okay, so we have to specify those 3 elements, and then we just call .compile on my model. So my model was my CNN, then I compile it, and now it's ready to train. Now all that's left is just called .fit method. So fit method will take data in certain configurations. So my data could be in the form of NumPy arrays, and .fit will automatically convert it to tensors. It could be in tf.data.dataset, which is a kind of an iterator you can look more into. So you can define this and pass that into fit, or you can create a data generator yourself. So if you're familiar with iterators and generators in Python, you can define a data generator yourself and pass that into fit. It will accept any of those. And then, so here we're doing exactly that. Our training images are numpy arrays, and then labels are also numpy arrays. So this is actually fit expects like X, which is our input, and Y, which is our output. Just make sure this is correct, X and Y. So it needs to know what is the input and what is the label for that input or the output that it, and then we can specify the batch size, which is a lot of times all of the data will not fit into the memory of a GPU. So you need to look at smaller batches of data at a time. And then epochs define how many times you want to go through the entire data set. Okay. And then additionally, if you have set aside a small amount of data set for validation, you can also pass that as validation data. And what would happen is after each epoch of training, it will run inference on the validation data set and also print out the loss and accuracy for the validation set. So this is nice to make sure that your model is not overfitting, to make sure that the training loss and validation loss are close to each other. So basically a couple of lines, and after you've defined your model, you can start training it. This is like topmost level of way of training a model. Now, once you train it, of course, it will give you back a history object, which is basically a dictionary that tracks the loss and accuracy at the end of each epoch. So since we trained for 2 epochs, we should have 2 values for each. So you can also like plot these and see what's happening. That's nice. And then 2 other convenient functions, which are very similar to fit or evaluate. So this is for inference. You can run on test images and labels. And then it will give you back loss and accuracy on the test data set. If you don't want loss and accuracy, but you actually want the raw predictions, then you can also call .predict method. So if I run .predict method on my test images, I get a numpy array. So I had 10,000 images in my test data set. So that's why I have 10,000. And then I get a probability for each digit. So that's why the second dimension is 10. So I have 10 numerals, 0 through 9, and I get a probability for each numeral. Okay, so if you came to my last tutorial, you already know this. Right? This is what we did last time. But of course, there's a lot that's going on within the fit method. Right? So just going back to my last notebook, fitting involves first passing the input data through the network to collect the prediction, then putting that prediction and ground truth value into a loss function to compute loss, then computing the gradients, then updating the parameters based on a certain optimizer, right? And then repeating this over and over again. So there's a bunch of stuff that's going on within fit. And if you want to have more fine-grained control over what goes on inside this function, you can actually do that. Actually, forget what I said. Let's first talk about what if there are multiple outputs, right? So we already had this multiple input output model above. And it might be the case that your outputs are of different kinds, right? So for example, in this model, I was trying to predict temperature and humidity. Let's say temperature is a real number, but humidity is just a category, right? So low humidity, medium, or high. So those are 3 categories. So you might need different loss functions for both of those outputs. And you might also need different metrics for both of those outputs. So if there is a single output, it's very simple. You just define one of each. But if there are multiple outputs, how do you do that? Well, you just pass a dictionary, okay? So make sure you name your layers. So remember up there, I had given name to my output layers. This was the temperature and humidity. So now I can pass in the same names in my dictionary and specify the loss for each. So temperature should use mean square error, and humidity should use categorical cross entropy. Same thing with metrics. Okay, that was just an aside, just in case you were wondering how to train multiple input output model. Okay, back to having more fine-grained control over what goes on in fit. Okay, how do we do that? Well, that's very simple. We just have to note that we defined all these layers, and in the end, to define the whole graph, we called this function here, tf.keras.model. We specified what's the input and what's the output. This model class happens to have a bunch of functions inside it. So in fact, when we call .fit method, that .fit method comes from this class. So we can actually go into that class and redefine the fit method for ourselves if we want a more fine-grained control. So how do we do that? Well, we can define a custom model. And here we're just going to change the fit method. So the fit method uses train step function. And we can just write it out, right? So the train step will take data, which will be a tuple of inputs and outputs. And then this is what's going on inside the fit, right? So we open up a gradient tape scope. We compute the predictions. So now self here refers to the model, right? Whatever my model is, I'm just calling that on the input. I'm setting training to be true. So for example, if I'm using dropout, then it will work. Then I compute the loss to, based on my predicted value and my ground truth value, y and y pred. Then I need to compute the gradients of the loss with respect to all of the variables. So what are all of the variables? First, I need to collect all the trainable variables, which again, I can call model.trainable variables. Here, model is self, right? Because I'm calling this method on my model, so self refers to my model. So by calling self.trainable variables, I'm just gathering all of the variables. Then I compute gradient, tape.gradient of loss with respect to all of those variables. So this is a list. It could have millions of variables inside, depending on the size of my network. Once I have the gradient, now I need to update all of these variables. So instead of going through all of each variable one by one and doing assign sub, right, the way I did last time, I was subtracting step size times gradient from my variables. Instead of doing that, you can just call this self.optimizer.apply gradient. So I need to just pass in gradients and trainable variables into this, and it will automatically update all of the variables. So self again refers to my model, and outside somewhere, I need to define the optimizer for my model. So it will use that optimizer to apply the gradients. Okay, that's it basically, right? Within the gradient scope, get the predictions and loss, and outside then compute the gradient and update parameters. Then additionally, I can like track the loss. So I can like start a metrics instance. So I can track loss and accuracy, and I can update that. You can look more into what's going on here. I'm not going to talk in more detail about this, but this is basically to open up and show how we were getting these values here, right? So it was printing out loss and accuracy. Inside the fit method, this is what's going on. It instantiates a tracker for each of the metrics and losses. And then it, at the end, after every training step, it just updates the state and then returns the values for those. And if we have any metrics, then additionally, you can define this function here, just so that the metrics get reinitialized at the end of every epoch. If that doesn't make sense, no need to pay attention. Like, in fact, for now, we can just even delete this if this looks unnecessarily complicated. But that's the whole idea. So if you redefine your train step, then instead of calling tf.keras.model, right, like previously, let me go up here. Sorry, this is how I defined my model previously. So let's come down here. That's how I defined it last time, right? tf.keras.model, but instead of calling that, now I can call custom model, for which I redefine the train step and specify my inputs and outputs. Okay. And now, do I need to still compile it? Well, I mean, I already stated what's my loss function right here within the train step, and I specified my metrics up here. So I don't really need to specify those, but I forgot to specify my optimizer. So either I can like directly specify an optimizer within my custom model, or if I miss anything, I can like once again compile it. So this time I'm going to compile it, but only specify my optimizer, which I didn't specify in my definition. But loss and metrics are already there. Okay, so now I can call .fit method and it will work once again, right? It will still give me loss and accuracy because I defined those in the model, my custom model fit. And so now instead of calling the implementation that comes with Keras, it's actually using my implementation. And so now you can do, again, once again, more complicated things here, right? You can have if-else statements here. You can do bunch of complicated things, right? You can have like 2 or 3 different gradient scopes and have different kinds of computations depending on what your inputs and outputs are or your intermediate values are. Just gives you more control over what's going on inside the fit. Okay, so that's like one step deeper into. So basically, just to show that you don't have to rely, like if .fit method is not working for your needs, that's not at the end of the day, you can update the definition. And then the last is the most basic way. You just write the for loop and you don't really have to define any functions or anything. You can just write the loop and that works too. And that's basically how it's done, I think, by default in PyTorch. So let's do it the PyTorch way, I guess. Once again, let's define the same model. I'm just reinstantiating it so that it's not trained because we already trained it up there. I'm just reshaping my data set so that it has batches, because previously it was just one big NumPy array, and I want to like go, I want to like simulate going over batches. So you can kind of ignore what's going on here. Not really important, but if you use data generators or tf.data, then batching should be done automatically. So forget what's happening here. Okay, so now we're just gonna write out everything, right? Instead of calling .fit, I'm just gonna use a for loop. So for that, of course, we still need to specify what's our optimizer, what's our loss function. And important thing I need to mention here is you don't need to use predefined optimizers and loss functions, right? At this stage, you can define your own loss function, whatever it is. Just make sure it's differentiable. And you can define your own optimizer, right? So you specify those. Any metrics, again, if you don't find a metric already defined for you in the API, you can define it yourself. You can use those and then write out the for loop for training. So I'm just defining like how many epochs I want to train for. So I'll go through a for loop for that many epochs. And once again, this is kind of artificial. I'm artificially defining a data generator with a zip method. So it will give me batches of training images and training labels. But again, you don't need to focus on this. If you use directly a data generator, then you can just call this on the data generator, right? The essential thing is I'm just getting a batch of inputs and outputs from my data set. Then I open tf.gradient scope. I compute the predictions. So I just call my model on my input, setting training equals true, compute the loss function, compute the gradient. I apply the optimizer on the variables, update their values, which I specified here, so I can change them. I can add the metrics, keep track of those. Now I can do more things, like instead of just printing the loss at the end of epoch, maybe I can print it every 200 steps or something. And then of course, at the end of the epoch, I can give the average. And then reset the state for the metric. Again, these are not important. This is just how to deal with metrics. And then after each epoch, so this is for loop for an epoch. So once we have gone through the entire data set, that's the end of one epoch. At the end of the epoch, I can do inference on a validation set. which is very simple. Again, collect the prediction and then calculate the metrics and losses and print those out. So if you run this now, this is the first epoch. Every 200 steps, it will print out the loss and any metrics you wanted it to print. At the end of the epoch, it will go through validation and so on. So basically, you don't have to worry about custom model classes and redefining the fit method. If this looks simpler to you, then you can just simply write out a for loop and train like that. With that, I think that's it. Basically all I had for today, and I'm happy to take any last questions. So there's a question, were those half models new instances or references to the layers? So in the functional API, those were new instances, right? So I'm not reusing the layers, meaning that if I train one of those models, it's not that the state of those layers will get updated for the other models too. So those are separate instances. Another question, when do I need to change this loop? How general is it for using on different models? I mean, one thing I would suggest is like go to TensorFlow guide. So the entire tutorial I gave today can be thought of as an abridged version of this, right? All of these notebooks. So anything you want to look into more detail, you can go into one of these. And you can look into how to train, for example, a GAN, right? So for a GAN, what you would do is it will have two parts, a generator and a discriminator. So for example, you will start a gradient tape for the generator. You will generate some images, calculate the loss, update the parameters for the generator. Sorry, for a discriminator, you will like discriminate some real and fake images. Then you can go to the generator, generate some images, make sure your generator is set to trainable, but your discriminator is set to false in the second gradient tape. And then you apply gradients once again, right? An optimizer. And that will just update your generator's weights and not your discriminators. So if your model has like these two parts, you would not be able to just directly use .fit method on it. You can go to like lower level here and define your logic of training here. So that's one example I can think of.
Okay, Asad, thank you very much. We really appreciate you taking time to prepare this tutorial and going through it. Thank you. As somebody was saying, super amazing. This is a really great tutorial. Thank you.
Thank you.